Hello everyone, welcome. We're going to talk about graphs, yet another kind of data structure. Here you see two graphs, graph G1 and graph G2. So let me explain what a graph is. So a graph is a data structure which contains a set of vertices or nodes. We call that set V, and another set of edges or arcs that we call E. So here, as you see, I just wrote it in the red line that usually the set V or the vertices are non-empty set. However, the set E or the set of edges can be empty. That means that we can have a graph that there are some nodes that which are not connected to each other. So edges are, as you see here, are the connections to vertices. In the graph G1, we have the set of edges called E1, and here you can see the very first edge I wrote here is A comma D, which means there is a connection between the node or the vertex A to the vertex D or the node D. On the right side, you see another example, the graph G2. Also, it is a binary tree. We have talked about the binary trees in other videos, so make sure to watch my other videos about binary trees. So here, the node A is connected to the node to nodes B and C, and also B is connected to node A, D, and M, and so on, as you see here. So here, there is one way or two ways of there are two ways of showing in a graph. One way is to draw a graph, which is going to be easy for like the graphs with just a few number of vertices and maybe a few number of edges. The other one, as you see here, is using like the sets V and E. Again, for like the number of like when we have the a few number of sets or still number of edges. Still is possible to use this one as we might have like some larger graphs or the graphs with more vertices or more edges. It's going to be harder to actually draw the graph or using this set of vertices and edges as we see here. Another way of showing a graph or representing a graph is using a matrix, so that it can be really easy to store data of like a graph using a matrix. So let's say that how for the graph G1 and how for the graph G2 we can actually draw the matrix, as we call it, adjacency matrix. So in the adjacency matrix we are using the numbers 0 and 1, and 0 means there is no connection and 1 means there is a connection between the two vertices. So here for the graph G1, and I'm going to write down the name of the vertices, both in this row here, also this column here. We're going to have A, and then we're going to have B, C, and D, and then K. Here we have A, B, C, D, and K, and that's going to be the number of rows and the number of columns. So as you see here, the node A is not connected to itself, so then we're going to put 0 here for the connection between the node A and itself. And there is no edge from A to B. Also A to B will going to be 0, and from A to C there is no edge, so it's going to be 0 from A to D and K. All there is, so that's going to be 1. So 1 again means that there is an edge, and the 0 means there is no edge. For the node B, is only connected to the node C, so it's going to be only one here, and every other entry will be 0. For the node C, is connected to node B and D, so here 1 and 1, and the rest of the entries will be 0. For the node D, is connected to nodes C, K, and A, except node B. For node B is 0, but for every other 1, it is 1. So making sure that for the node D, except itself, it is going to be 1. For the node K, it's connected to the node A and D, so these are 1, and everything else is 0. So that's adjacency matrix to present a graph, so it's going to be much easier to store or to represent a graph using these matrix rather than just maybe drawing a graph or maybe use the like the set of vertices and set of edges to show that. Same thing for the graph G2. For sure we can just draw a very similar and simple matrix. The node A, B, C, D, M, F, and K. Here also we're going to have A, B, C, D, M, F, and K. So here again, as you see, A is connected to the node B and C, and it's not connected to any other node, so it's going to be 0. The node B is connected to A, and also the node D and M, so every other entry is 0. The node C is connected to the node A, and it's connected to F and K. So here's going to be 1, and every other entry is going to be 0. The node D is only connected to node B, and every other entry is 0. The node M is also connected to B, so every other entry is 0. And the F and K only connected to the node C, so every other entry is 0. So that's our like the graph, like the graph that we have here for like the graph G2 as well. So there's interesting features about like the graph G1 and graph G2. As you see here, and if you look at the adjacency matrix of the graph G1, so I'm going to just zoom in so you can see better here. Actually, the matrix is symmetric around the main diagonal. So if again, this is the main diagonal that we have here. So as you see here, the like the matrix is symmetric, and that's what we call, or that's the case that happens all the time for the graphs which are not weighted, okay, for the graphs that are not directed. So a graph that is not directed, when we show it using adjacency matrix, the matrix will be always symmetric. Same thing for the graph G2. As you see, it's also like the undirected, so there is no direction from the for the edges. So as you see here, it's also symmetric around the main diagonal. So that's a very good and important feature when we like to draw even. So that's going to be even easier to write down. So it means that we only need to fill half of the like the entries, and like the the other one that's going to be mirrored will have the same like the value. So it's going to be even like the shorter, or like we're going to save memory when we're going to store the like the graphs information. So as I said, these two graphs G1 and G2 are undirected, which means that if there is an edge from any two between any two nodes, that's a mutual like the connection. So from A to B, if there is an edge, also there is an edge from B to A, as is the case in the graph G2, that there is an edge from A to B and also from B to A. But just for the sake of simplicity, we're not repeating the edges AB and BA. We're just writing AB, and it means that there is an edge between A and B. So it means that here, as you see in the adjacency matrix, inside for this set of edges E2 and E1, it doesn't matter if we write which one first. So A comma D is as same as like D comma D, so it's going to be the same edge. However, if the graph is directed, okay, this example I'm going to write here. So if your graph is directed, something like this, I'm going to write here. For example, here we have A, and here we have B, and here we have C, and here we have D. As you see here, there is so if we're going to write the set of vertices, so first of all V, and let's call this graph the graph G3. So V3 or V subscript 3 will going to be A, B, C, and D. So that's a set of vertices and set of edges. E3 this time we're gonna be A to B. So the very first one is the source, and this is one the destination. So B is the destination. And then here we have the edge A to C, and then here we have the D to C. If you look at this graph, there is no edge from C to D, so we're not adding that one to the graph that we have here. If, for example, we're going to add another edge, such as this one, like the B to A, and then what we need to do, we need to go here and add also that edge to the the set of edges that we have here. So that's going to be then the B and A edge as well. So that's the graph of graph which is directed. Not only graphs can be directed or undirected, we also can have graphs that have weights associated with each node. For example, with each edge. For example, we can see these nodes as the cities, and also the edges can be the distance from each node to another one, or from one city to another city. That can be like the weights. And as we also see, sometimes there is like this a path or the route from one city to another one, and like the opposite way has its own like the road, so the weights can be different. So here I'm going to draw another graph. Let's call it the graph G4. So the graph G4, and I'm going to make it both directed and weighted. So here's the node A, and it's connected to the node B here, and C, and then here we have D, and I'm going to just draw some edges here just to show that how they are working. And here is this one here with the like the weight. So 5, 2, and then here we have 8. Here is, let's call it for example 4, and then here going to be 7 and 6. Now if you want to show the graph G4 using the set of vertices, like it's going to be, or an edges, it's going to be V4, which is going to be A, B, C, and D for sure, and then we're going to write the E4. This time we're going to use the tuple rather than just a just a pair. So we're going to have, there's an edge from A to C with the weight 4, so it's going to be A, C, and 4. And then there is an edge from A to B with the cost of 6, or with the weight of 6, A, B, and 6. There is one from B to A, so it's going to be B, A with the weight of 7. There is one from B to D, so it's going to be B to D with the weight of 2. There is one D to B with the weight of 5, and there is one from D to C with the weight of 8. So this weight again can be cost, or it can be the benefit. So depending on what we are defining for like these numbers or these weights, we can just use either positive numbers or maybe negative numbers. We also can show the graph G3 and G4 using the adjacency matrix. So for the graph G3, this is gonna be the adjacency matrix. Again, we have only 4 vertices, A, B, C, and D, and here we have A, B, C, and D. So there is an edge from A to B and C, so to 0 and B and 1, and there is 0 to node D. From B to A, as you see, also there is 1, so I'm going to use the this red marker here, and there is that's only 1, so, and everything else is going to be 0. From node C, there is no edge to any node, as you see, it's going to be all 0, and from D is only an edge from to C, and every other entry is going to be 0. And as you see here, this adjacency matrix that we have here is not symmetric anymore, because as we see here, there is no edge from C to A. Also, there is no edge from C to D, so it's not symmetric. Although it does not mean that none of the directed graphs are non-symmetric. For sure, we can have graphs directed and symmetric. That means that if there is an edge from A to B, two random vertices such as A and B, there should be, if there's an edge from A to B, there should be also an edge from B to A. Now, look at the graph G4, and we're going to write the adjacency matrix for this one. The only difference here is that instead of writing the numbers 0 and 1, we're going to actually write the weights associated with each edge. So there's no direct edge from any node to itself, so I'm going to put 0 for these entries or in the main diagonal. And then if there's from the A to B, which the cost of or the weight of 6, from A to C it is 4, and there is no edge from like the A to D. So what we can do is that as a we can have a contract. For example, if there is no edge, maybe we can put the weight to be equal either infinity or maybe 0 or maybe some other number. So let's just use infinity, means that the cost or the weight or benefit or whatever, again, it depends on that. So if it's a cost, we can put the cost we're going for infinity. If it's like the benefit, maybe we can put equal to negative infinity. So again, it depends on the way that we're going to define these weights. So B to A, as we see here, the cost or the weight is 7. B to C, there is no, so we're going to put infinity. And from B to D, the weight is 5. From C, there is no connection to any other node, so we're going to put infinity for all of them, as you see here. And for the D, there is one for C with the weight of 8, and D to B with the weight of 2, and there's no edge from D to A, so we're going to put infinity for this one. As you see here, this matrix also is not symmetric, but again, it doesn't mean that like all weighted directed graphs are non-symmetric. We can also have symmetric graphs. If you have looked at all these examples that we have provided so far, the graph G1, G2, G3, and G4, all the main diagonals have the value 0. So 0, 0 here, same thing for the like this one. I need to just fix this drawing here. It's not very precise here, but the main diagonal is 0 because there is no edge from like the node to itself, so it's going to be from K to D, that also was 1, so here is 1. So as you see, the main diagonal also here is 0, means that K to K is 0, D to D is also 0, C to C is also 0, B to A, B is also 0, and A to A is 0. So that's our main diagonal, as you see here, and all the values are 0. Same thing for the graph G2. As you see here, all the like these values are like the 0, so making sure I'm not making a mistake here, B and B, and again that's the main diagonal, and all values are 0. So when like the main diagonal of adjacency matrix is all 0, means that there is no connections or no edge from a node to itself in the graph. So all the graphs are connected to all other nodes, and they are not connected to themselves. If there is an edge from a node to itself, then that's called a reflection. So it's a reflexive, so we're just having a node to itself, and that means that the entry inside for the main diagonal will not be all zeros anymore. If there's an edge from one node to itself, then we're going to have like an entry rather than 0 to itself. So and again, is as a contract, we can say the weight from one node to itself, if there is no direct edge, gonna be 0, or again we can assume that it is infinity. So it all depends on the way that we're defining the weight, especially in the weighted graphs. In the unweighted graphs, we can use like the 0, again just to mention that there is no edge from that. If there is one, means an edge. So again, really easy to draw a graph that uses this reflection or reflexive edges. So here we have the graph G5. Here's the node A, B, and C, and the node A, as you see here, has an edge to itself. And let's also make this one also directive. So here's the node A, B, and C. I can just draw a simple one. So from A to A there is, and from A to B and C there is. There is no edge. Let's also put one from B to C just to have some entry also here. Here is 0, B to C, B was also 0, B to C is 1. But for the vertex C, there is nothing, so it's all gonna be 0 as we see here. Now let's learn about some terms about graphs. So let's, after we learn about the edges and the vertices or nodes, we're going to see what is a path. So a path is the edges from one node. Let's call it, for example, the vertex or the node V1, we subscript 1, to another vertex in the graph. For example, we subscript n, and this is a sequence of all the edges we need to pass in order to reach that like the vertex. If you look at the graph G1, this can be a graph, so I'm just going to draw that one. So for example, from A to D, and from D to C, and there is C to B. So we can say that there is a path from the node or the vertex A to the vertex or node B. We're passing the A to D, and then from D to C, and then from C to B. So here, as you see in the graph G1 and graph G2, both of them are undirected. And so easily we can just go from A to B, and also we can go back from B to A easily. If the graph is directed, there is no guarantee that this is the case all the time. For example, if you look at the graph G3, there is a path from the node B to C, which is, I'm going to write here. So as you see, there is an edge from the node B to A, and then from like the A to C. So there is a path from B to A. However, the vice versa is not correct. As you see, there is no way that we can go from the node C back to the node B, because all the ways goes into the node C, and there is not outgoing edge from like the node C. So that's about the path. We're gonna also learn about a circuit and also a cycle, and the difference between a circuit and a cycle. So circuit and also a cycle, both of them are path. A circuit is a path in which that the source and the destination are same, and none of the edges in like the path that we had are repeated. So that's called a circuit. If in addition to the condition that no edge is repeated, none of the vertices also repeated in the edges or not visited more than once, that's called a cycle. For example, if you look at the path from A to A itself in the graph G3, as you see here, we're going from A to B, and then we're going back from B to A. So as you see, none of the edges are repeated. Also, none of the vertices except the very first one, which is node A, which also is the last one, are unique and distinct, so that is a cycle. So from A to B, B to A, that path is a cycle. Also is a circuit because also none of the edges are repeated. We also talk about the weights in the graph. We can also maybe show more example of like this circuits and cycles. Maybe it's good to just to see example of both. So here is the graph A, then B, and here we have the node C here, and then here maybe I'll just have that one, and maybe that's not bad actually to have that one. So I'm going to just have these two, and here, and also here. So one cycle here is going from A to B, so A to B, and then from B to C, and from C to A. And as you see here, none of the vertices or edges are repeated, so that's a cycle that we have here. So here, and none of the like the vertices, as you see, are repeated. So one other thing that we could do, if you want to show an example of like this, maybe a circuit. So we want to like draw another one. So A, B, and C, and D. So here I'm going to draw this one here, go B to C, C to D, this one, and to A. So as you see here, there is a circuit from A to A itself, going from A to B, and from B to C, from C to D, and then from D to C again, and then from C to A. So it's a circuit but not a cycle, because as you see here, the node or the vertex C is visited twice. However, none of the edges are repeated, because then the edge from D to C, this one, and C to D are two different edges, and they are not the same like the edges. So here again there are some, but so we learn about the cycle, we learn about the circuit, we also learn about the path. So let's see what is a complete graph. So a complete graph is a graph in which all nodes or all vertices are connected to every other vertex or node in the graph. So here is a complete graph with only two vertices or two nodes. Here's an example of undirected one, which is A is connected to B and B is also connected to A. For directed one, we can have A and B here, and A is connected to B, and B also has connected to A. So that's for both connected and directed and undirected. With three nodes or three vertices, we can draw this one. So as you see here, there are two vertices, two edges from any node to other one. Here we have for directed one, A, B, and C. And also I'm gonna write this one here. So let's see if we can find actually a pattern to find the number of edges and number of nodes in a complete graph. So as you see, if there are n nodes or n vertices, each node is connected to every other node, which means that each node is connected to exactly n minus one other vertices. So if one node is connected to n minus one vertices, then the total number of node like the edges will be n times n minus 1, because again that's for every node that we have. However, in undirected graph, we actually counted each edge twice. So if you see here, we said, for example, from the node A to B and C there is an edge. So there is one, and that's the second edge. However, when we wanted to count the number of edges for the node C, we counted this edge here and this edge here twice, because for each one. So we need just to divide the total number of edges by 2, or that number, to get the actual or correct number of edges for the ungraphs, for a complete graph. So the number of, or the size of the edges, and that's how we are showing that, it is equal to n, and again we can show n by v. So this is v times v minus 1 divided by 2 for the undirected graph. If it is a directed graph, we actually don't need to divide by 2, because the edges are distinct. So if there is, as you see here, this is the one edge from B to C, and there is one from C to B. So they are distinct. So we're not dividing by 2. For a directed graph, the number of edges will be equal to V, or the like the size of the vertex, said vertex, times V minus 1, and that's going to be the number of nodes in the complete graph. So one of the things before we end this video is about subgraphs. So I'm gonna just draw a very simple graph. Look at this one here, for example, A, B, C, and no matter if it's a directed or undirected, we can always create subgraphs. So subgraph of graph G, and let's say this is called the graph G5. So we can see that graph GC is a subgraph of the graph G5 if you have something like this, and the node C also here. So in the that's and also how we show the subgraph. So if we have the graph G5, for example, with the V5 and E5, then we say that the G6 is a subgraph of the graph G5 if like the V6 is part of the subset of V5, and also E6 is a subset of the set E5. Again, as we learned, V and E, both of them are sets. V usually is non-empty because we're going to have at least one vertex in the graph, and E can be like the empty if we have like the graph that doesn't have any connection to any other node. So one other thing that also I wrote the example at the very beginning, but we have not talked about it is this graph G2 that we draw here. So if you see that I said it is also a binary tree, so any graph which does not have a circuit is called a tree. So graph G2 is a circuit. As you see here, there is no path from a node to any other node that will come back to itself. So node A, if I want to go from node A to any other node, there is no way that I can go back to the node A. So from node A, I can go to the node C, and from node C to K, and that's it. That's going to be one way, like the direction. So it's not a it's not a circle. That's we see here. So that's like the like the general discussion about the graph. So we discuss about the graphs, about some terms, about the subgraphs, and about the complete graphs. And in my other videos, I'm gonna talk about talking more about the graphs and some algorithm and some problems associated with graphs. Make sure to watch my other videos about the trees, also about the graphs and data structure as well.